See, we've got about another 30 seconds before the time. But just out of interest, how many, how many of you have this as the first Java one they've ever been to? Cool. How many have been to a previous Java one? Okay. So, audio, can you test for the back? Can you guys hear me better now? In the back? I'll try, if I speak louder, does it reach? Okay, I'll try and do a little louder on the voice, but if you can pick it up a little there, because that's above normal voice level for me. Okay. Well, it's good to see so many fresh, first time in Java 1 people. That's an interesting mix for the audience. Usually we get about a 3/4 to a quarter ratio, but this is good. Subject we're going to talk about is right up there. Hopefully you're in the right room. I'm Gil Tene. We're talking about garbage collection in Java. And just to set the right expectation for the talk, there's a little bit of echo, at least for me. To set the right expectations for the talk, this is not a how to tune GC talk. This talk is focused on how GC works, on how the machine works or how the mechanisms work. And the idea is that if you can understand what garbage collection does in general, in the various stages and techniques and terminologies, and then you can apply your own brain to the tuning exercises that will happen later in real life. So rather than giving you a set of flags that are good for 2017 for a specific collector in a specific version of Java, in a specific version of your application, I'm going to try and get you a feel for what garbage collection actually behaves like so you could do the job on a regular basis. And that's the real purpose here. You learn enough to be dangerous, and you will get dangerous, and that'll come with pain later. Now, I work at a company that makes JVMs and garbage collectors, so I'm really, really proud of that. And I promise that I will keep that part of we make the best garbage collector on Earth pretty much to the end. There will be a lot of generic, useful education here that's good for any JVM or any garbage collector actually in the runtime. So agenda-wise, the way we're going to cover this is we'll start with fundamentals, terminology, and mechanisms. We'll then go and classify all the currently available production garbage collectors and JVMs, or most of them. And then we'll talk about the stop the world problem that exists with garbage collection, and then talk about, what a world where that is solved and doesn't happen anymore looks like, which, like I said, I'll keep to the end. A little about me. My name is Gil Tene. I'm the CTO at Azul Systems. I've been working on garbage collection as a problem for around 15 years now. And here's some evidence of me working on garbage collection. For those of you who don't recognize that, that's a trash compactor. It's in my kitchen. The job of a trash compactor, if you think about it, is to perform minor GC compactions during the week, so you only do a full GC evacuation once a week with the garbage guy walking outside. And that works great, here in California at least. But in this case, it stopped working. There was a bug in it. You can see that fragments were falling out the back. I had to go and open and manually defragment the heap of garbage in there. That actually happened. And I thought it would be funny to take a picture with the actual garbage collection book. But the most important thing about this picture is that it was taken in 2004. So I've been thinking this is really funny for 13 years. I'm lazy and I recycle in any new pictures. And I used to look better, I think. So I've worked on various garbage collectors, including our garbage collector called C4, and a pauseless collector. I've built a lot of things, physical machines, virtual machines. I've helped design CPU, instruction sets, and operating systems and drivers and runtimes, obviously, and all the way up to nation scale enterprise applications with tens of millions of subscribers and all that comes with that. We had to build an app server to make that happen because they didn't have them then. So I've made a lot of mistakes, and some of those I teach people about. But unfortunately, not, people usually learn from their own mistakes. I'll just make funny jokes about other people's mistakes then. A different subject that you'll find me talking about a lot is the notion of latency and response time, how it's measured, how it behaves. You can find a bunch of stuff online with me talking about that too. So enough about me. I'm going to do one more little raise your hand survey at the beginning. I'd like you to kind of start raising your hand and keeping them up as I get to a number that you recognize. Raise them and then drop them after. How many of you use Java with heaps that are half a gigabyte or more? Okay, that's most of the room here. The rest of you are really tiny. Now, how many have more than a gigabyte? Keep your hands up. If not, drop them up. How about more than 2 gigabytes? More than 4 gigabytes? Look around. More than 10 gigabytes? Ooh, now look around. More than 20? 50? 100? Okay, I want to talk to you afterwards. Now, but the reality is any of these matter. Let me show you a magic trick. I was guessing that this is where we're going to group. This guess has been correct for the last 10 years. I've been doing talks around this for about 10 years, and that hasn't moved. The vast majority of this room dropped their hands at 10 gigabytes. That's an interesting observation about the fact that we don't actually make use of memory and growth of memory, and the fact that in the last decade, we actually got 100 times the memory for the same price, but we still kept the sizes the same. That's a big observation, and a huge reason for that, in my opinion, is garbage collection. Okay, so background. Why should you know how garbage collectors work? Not just how to tune them and what flags to use. Why should you know a little bit about how the machine works? I like to use practical stories. This actually happened to me. And I call it the story of the good little architect. Any Mark Twain fans here? You might recognize the theme. And I define a good architect not by the quality of their architecture, but their ability to actually make people build architecture. If you come up with the best, beautiful architecture you can think of, but nobody actually adheres to it, you're not an architect. You're a philosopher. Architects actually get people to build their stuff, or at least the successful ones. And early in our career with Pauseless Garbage Collector, we actually ran into a very successful architect. And along with that, we ran into an 18-second pause in a pauseless collector, which was very embarrassing. This was back in 2006 or so. So we went and dug in to see what's going on here. And when we dug into the application to see what's going on, we found some surprising behavior. This application had behavior that we normally didn't see. And every time we did a garbage collection, we found that we had to execute tens of millions of finalizers every time we collected, which at least at the time was very abnormal. Because it was abnormal, we didn't bother to make that a concurrent operation at the time. Since then, we fixed that a long time ago. So now even this won't pause. But it was curious. We were trying to figure out where this comes from because we just don't see that normally. So we dug into the application with the customer, and we found out that every single class written in a project that ran for about 18 months, over 10 people, had a finalizer in it. Every single class that this team wrote had a finalizer. There was a very good architect at play here. Nobody got away from doing this. But more interesting was, what did the finalizers do? Anybody want to guess what the finalizers do? What is that? Exactly. So the finalizers were putting nulls in all the references to help the collector out, because you don't want to, if this object dies, you don't want to keep references to other objects, right? Let's help the collector out by putting nulls everywhere. Well, this is the worst possible thing you can ask a collector to do. It doesn't help it, it hurts it. But there is a world where this is exactly the right thing to do. In C++, this is how you write Ceph code. You have destructors, or the equivalents. You make sure that if you die, you kill everything you touch, so reference counting will collect those too, and whatever else you're doing. And if you actually don't adhere to this kind of architecture, you're going to have memory leaks and corruptions and all kinds of other bad things happening. So you need destructors on everything in C++. In Java, you never want destructors or finalizer unless you absolutely can't get away from doing them. And even then, you should think 3 times before doing it. So this is the wrong thing for Java or any garbage collected language, and it's the right thing for reference counted languages with destructors. Why? Because collectors work in certain ways, and we'll get into that. Hopefully it'll become evident why this is a terrible, terrible thing to do in a collector. It's not just bad practice. It's like 1,000x more expensive for the collector to deal with, or more. Okay, so upping this a little more, in general, I find that there are a lot of myths and misunderstandings about collection. A lot of what people think about collection, garbage collection, is wrong, and most of the advice you will find on the internet is the opposite of correct. So even when you read my stuff, you should suspect it. But academic work tends to be pretty good. Peer-reviewed academic papers tend to be pretty good, but general internet advice tend to be terrible, especially 3 years after it was written. So, and Google doesn't forget. So here are some basic things that are different than what you might think. So for example, garbage collection is a lot better than what people think at a few things. For example, garbage collection is actually the most efficient possible way of managing memory. It is cheaper than any other alternative when it comes to cycles spent per allocation and removal of dynamic things. GC is cheaper than malloc, period. And we can prove that. I'll get to a proof later. Okay, I know this is controversial. That's why I wrote it there. The other one is the garbage collector basically doesn't spend, an efficient garbage collector doesn't spend any actual work looking and thinking about that object, which is why asking to finalize objects is a terrible thing, because you're asking it to take something that costs it nothing and actually do an operation per object. And then the last part is the garbage collectors, at least in Java and most modern runtimes, will absolutely find all the dead objects. They don't need help. They don't need you to break cycles. You don't have to worry about linked lists that point to themselves and weird graphs of objects. If it's dead, it's dead. You don't need to worry about it. They do a perfect job, a precise job of finding the dead objects, and helping it out with putting nulls is just getting in its way. Doesn't make it more correct, it makes it more slow. But there are a lot of things that are worse than what people might think. For example, if your garbage collector has any form of stop-the-world operation to perform its work, like normal work, I don't care if it's rare or not, it will pause for something in the order of a second per gigabyte of live stuff that you have. You can't get away from that. You can delay. And yes, there are some collectors which will actually not do that. Zing is one example. There's others in the works. Hi, Shenandoah. Yeah. But fundamentally, if you're doing compaction and stop the world, you will see this pause. You cannot get away from it. I don't care what other people tell you. Now, you might be able to get away from it for an hour or a day or a week, but it is there. It's just swept under the rug. Beyond that, not all memory leaks disappear with garbage collectors. We take care of a lot of memory leaks that are common mistake bugs that happen in other environments, but fundamental leaks of forgetting to forget are still there. If you just keep accumulating stuff, it's going to grow. It's not a magic bullet. The last one here is very important, testability. Garbage collection tends to work in the opposite direction of what people want from testable systems. Most of our tuning in garbage collectors has been focused on pushing bad problems to the future, making them more and more rare, not eliminating them, but pushing them forward. And that means that when you've tuned your system to finally pass a 20-minute stress test, you haven't actually gotten rid of any problems, you've just moved them to minute 21. For QA, this is a terrible thing because a well-tuned GC system often takes days or weeks to actually test, which is where some interesting tools that help you cause the bad GC things to happen while you run might be interesting to use. Okay, let's talk terminology. Basic terminology starts with classifying the collectors. How many of you know what a parallel garbage collector is? Okay, a bunch of you. How many of you know what a concurrent garbage collector is? Notice that it's fewer than the parallel. There's a reason. Those two words are synonymous in English. There are some languages, I grew up speaking Hebrew, where there's only one word for both of these. But in garbage collection classification, they're orthogonal. They don't mean the same thing. A concurrent garbage collector is a collector that does its work while your application is running. The garbage collector and your applications are concurrent with each other. We often call you guys the mutators. You're mutating the heap, you're changing its shape. A parallel garbage collector is a collector that uses more than one thread to do its job. It can use more than one thread, more than one CPU to do whatever it is it's doing. These things have nothing to do with each other. You could be concurrent but not parallel. You could be parallel but not concurrent. You could be neither. You could be both. These are just definitions of terms. Unfortunately, if you read maybe 30 years back in garbage collection papers, you'll find these terms actually interchanged. What used to be called parallel is now called concurrent. But this is probably good for the last 20, 25 years of academic work, at least, in garbage collectors. So keep in mind that parallel and concurrent are very different things. Now, what is a stop-the-world collector? Well, stop-the-world is the opposite of concurrent. Rather than run concurrently with your application, it stops the world and it runs. And then you get to run later. So these are direct opposites. A monolithic collector, or a part of a collector that's monolithic, is a collector that does all the work in one chunk, in one piece of work that you cannot break into pieces and maybe do in pieces and run in the middle. So all or nothing. An incremental collector is a collector that can take the work you need to do, chunk it into smaller pieces, do a little bit of it, maybe stop the world, do a little bit of it, then stop stopping the world, let you run. Then do the next chunk and the next chunk and the next chunk, interleaving its work with the application, but not concurrently. It stops you and does a little, you run some and it doesn't do, interleaving. Incremental collectors are usually stop-the-world incremental collectors. But there's one very important technical word in garbage collector classification. And it is used honestly in academic terms mostly, but it's been kind of abused from a marketing perspective. That is the simple English word mostly. Mostly means exactly what you think it means, but you need to carefully read any sentence that has the word mostly in it. Mostly concurrent means sometimes not concurrent. Mostly parallel means sometimes single thread, and mostly incremental means sometimes monolithic. Mostly is usually what you put in front of a really nice thing to say I'm not doing that. Or, hey, I mostly do that, but I was honest with you, I said mostly. You'll find that in a lot of classifications. Okay, let's talk about a few other terminologies, precise and conservative collections. A precise collector, well, let's start with conservative. A conservative collector is a collector that's not quite sure where all the pointers are. It's got to go and find junk in the heap, but it's not quite sure where all the pointers to everything are. Knows some, but not all. And it needs to, as a result, be conservative. Some things might be pointers, might not be pointers. We need to deal with that. A precise collector is a collector that actually does know when it collects where all the pointers are. And this difference is very fundamental because there are some things you cannot do unless you're precise. For example, a collector has to be precise if it's going to move an object from one place to another. If you move one object, point A to point B, you have to fix all the pointers that point to it. But what if you're not sure where they are? Maybe you left one dangling. Or maybe worse, here's something that I think might be a pointer, but I'm not actually sure if it's a pointer or an integer. Maybe it's just an integer that happens to have the value that looks like a pointer. I'll change my integer value because an object moved. Both of those are deadly mistakes to make, so you can't afford to do them, which is why, without being precise, you will not see any movement of The hard work to make a collector precise is not in the collector itself. It's the information given by the collector by the runtime. The collector just needs to know where the pointers are. But it's things like the JIT compilers and the runtime that needs to know at any point in code where the collector might collect where all the pointers are. So for example, at this point in the stack, if I stopped and collected, I need to know all the registers, if they're pointers, all the call stacks, if they're pointers or not. And if I move one code line, that changes. That information is carried in hotspot and what's called OOP maps and a few other runtimes as well, which the compilers and the JIT compilers produce. And next time you meet a JIT compiler writer, thank them for doing all that hard work that only is needed for this kind of stuff. Because without it, we wouldn't have precise garbage collection, we wouldn't have compaction, and we wouldn't run very long. All the JVMs we have today use precise collectors. They all move objects at one point or another. Okay? Safe points are these interesting things that we do in execution to allow these precise collectors to work. So we could theoretically have at any program counterpoint at any point what everything would be, but that's both hard and also hurts optimization. So what you do is insert safe points in the execution where we say, here we know where all the pointers are. Here we know where all the pointers are. Safe points are ranges of execution in the thread where we have full description of what the pointers are on the stack. Between them we may not, but there we do. There are all kinds of safe points, and GC safe point and safe point I'm using interchangeably here. There are other reasons for safe points as well. When I say that we bring a thread to a safe point, it means that we get it to that range of execution that we have a good description for and don't let it go past that point. Now that sounds a lot like stopping the thread, right? And stopping the thread is one way to do that. There's one key exception to that. For example, JNI calls. Anytime you call a JNI function, including blocking on a socket or a read or anything else, or anytime you block on anything, you actually enter a safe point. Now, entering a safe point doesn't mean you're not running. You could be inverting a matrix in C++ for the next 3 hours, but you are not changing any pointer states. You're not changing where the pointers are, so you are at a safe point. We have a good description for where you're doing. We need safe points to be frequent, otherwise we'll have what I call a time to safe point problem. I'm not going to get into it here, but it's fundamentally that, everybody's waiting and this one guy hasn't come back for the last 3 hours from a loop, and now we've got looks like a big pause, but nothing has started working yet. But there is a global safe point where we bring all the threads to a common safe point, and that is what is known as a stop the world pause. A global safe point and stop the world pause are the same thing. So we talked about some terms. Let's talk about some behaviors. Here are 3 things that all precise collectors in a practical term will do. One of them is they will identify all the live objects that there are in the heap. They will reclaim all the dead objects that they can prove are dead. And they will relocate objects from one place to another in the heap. Every one of these steps will happen in a precise collector. There's no real point in being precise if you don't do all 3. But let's look at concrete examples in classic simple algorithms that do these steps. The first one is a mark, sweep, compact collector. Marking is where you find all the live objects, that's step 1. Sweeping is where you identify all the dead stuff and somehow deal with recycling it, that's step 2. And then compact is step 3. 1, 2, 3, 1, 2, 3. But separately, there's a separate kind of collector called a copy collector, which doesn't do this as 3 steps. A copy collector fundamentally takes all the objects from one space, we call it a from space. Say, let's move all the live stuff to a 2 space in one pass. And when I'm done, I know that all the stuff is in the 2 space, so the from space is empty. That's a single pass that does all 3 of these things. Find the objects, move them, and as a result, I've reclaimed the dead space. So I'm going to break down the actual phases of the ones I just talked about as explanations so we can talk about them in a bit about their complexities. Marking or tracing. It involves starting from what we call roots. Roots are static variables, the threads in their stacks themselves, things that are the roots of visibility, pointers I can start from. And we start from these roots and we do what we call tracing or painting. Anything I can reach that has not yet been marked, I reach, I mark, and then I look inside of it and keep reaching. So I kind of paint and follow everything I can see, and everywhere I go, I mark that I've been there. If I get to a place I've already marked that, I need to go there again. Okay? So I start from the roots, and anything I can reach, I can reach. Now, at the end of one of these exhaustive tracing passes that starts from the roots, all the reachable objects, anything I can reach from my root set is going to be marked live, and anything I can't reach from the root set will not be marked live. And there's a very important quality here. If I cannot reach it from the root set now, I will never be able to reach it from the root set again. To be able to express a reference to an object, I need to be able to reach it before I express it. So copying a reference from, it's only reachable things. So once I've shown that something isn't reachable, it is dead. It's not becoming alive again. This is why a circular linked list doesn't have to be tagged and broken, because if I can't reach into it, it's going to be dead. It doesn't have to break things apart. So that's tracing. It's exhaustive, but from a complexity point of view, its work grows with the live set, with the amount of live objects and live references we have to move through, but not with the size of the heap. If I have a 20 gigabyte heap or a 100 gigabyte heap and I only have a 100 megabyte of live stuff, I'm only marking the 100 megabyte of live stuff. The size of the heap has nothing to do with the complexity of the mark. But if I double the live set, it will grow. So it's linear to live set. Sweeping is a very simple mechanism. Imagine I just did a mark, and everything that's alive is alive, and if not, it's not. We sweep through the whole heap, looking at all the objects, and if they're not live, we somehow deal with them, recycle them, or mark them for recycling later. Putting them on free lists is one common way to do that. So go through everything that's there, put it on free list. We'll deal with it later. This is obviously a simple pass. You can parallelize it or not, but its work is linear to the size of the heap. I have to manage and visit every single object, regardless of if it's dead or alive. If I double the heap size, I double the work. Changing the live set has no effect on the work, really. Not significantly, at least. Okay, so once we've marked and swept, and we know where all the dead stuff is, we have compact. This is a simple mark sweep compact algorithm. Let's start with why do we need to compact? People often argue about this, but I think the arguments are settled probably 20 years ago or more. The reason you compact is because if you don't, over time your heap will get Swiss cheesed. You'll end up with holes everywhere. And even though the heap is 90% empty, you have no place to put your 11 kilobyte string, because the biggest hole is 9 kilobytes. There's 100 gigabytes of free memory, but no hole big enough for your 11 kilobyte free. And that would be very embarrassing if we threw an out-of-memory exception at that point. Right? So because of that, we have to compact. Now, the reality is, in the real world, when you have variable size objects with variable mixes of size going over time, you will fragment the heap. It's unavoidable. There's no real argument about this in the general term. It's just a question of how long can you live before you have to do this thing. That has a lot of argument about it, or variations about it. But anyway, we will need to compact. So what does compacting mean? Well, compacting means moving objects together to make bigger holes. And there are various techniques for doing that. For example, you can compact in place, which is what the mark sweep compact collector in the parallel GC does, which is, think of it as, we marked everything, we swept everything, move all the live stuff to the left. That's compacting it to the left, then I'll have all the empty stuff on the right. It'll be contiguous. So we basically are going to move stuff together to get all the empty stuff to be big. And it basically has to then not just move the objects, but we move the objects, we have to fix all the pointers to those objects. So we got to somehow track them and pass and fix them. That's a compact in place. There are evacuation compactors that take a region of memory and move all the live stuff out of it, and now the region is empty. It's a similar technique from marking and then fixing up the references too, but in a slight difference in behaviors we'll touch on. The fix part is very important. If I moved one object, that object might have a billion things pointing to it. So I have to scan the heap for every possible pointer to this object and fix it, which which is why we never ever move one object, because that would be very inefficient. So we tend to move a lot of objects together, or most of the objects together, because then we get to do one pass to fix everything up together. Complexity-wise, even though this is a pretty bad and heavy operation, it's only linear to the live set. I only have to move the live objects, and only have to fix the live references. So growing the heap size doesn't actually change the work here. Growing the live set absolutely does. Okay, the other type of collector I talked about, a copy collector. This one takes objects from a from space and moves them to space, starting from the roots, moving everything it can find, puts it in a to space, and at the end we have an empty from space. It's actually very effective, very efficient. It's a single pass, linear only to the live set, and is actually a very commonly used collection for some mechanisms. However, a thing to keep in mind here is it needs a to space. And the to space, in a simple, without making other things happen around it, collector, needs to be as big as the from space. Because we don't know anything's dead. We might have to move everything, and this is usually monolithic. You start, you move everything. You can't leave anything behind. So the to space needs to have room for all my stuff, which is as big as the current heap, because I don't know how much is dead in there. That's the simple one. So looking at some of the qualities, copying requires 2x because of what I just said. A mark compact without the sweeping, an evacuating mark compact might need 2x the memory to do a full compaction, but it could stop in the middle because it's doing a region at a time. A mark sweep compact with compacted place doesn't need extra memory to compact. That's a nice plus. Both copy and mark compact are linear only to the amount of live stuff. It's the sweep that grows with the heap. Mark sweep compact is linear also to the heap. And then mark sweep and sometimes compact, I didn't talk much about, but that's a common attempted technique. Delay the compact if you can. Then I talked about the monolithic part of copying. Let's talk about generational collection that brings some of these things together. I talked about the efficiency and the linearity of these algorithms for a reason. Generational collection is a really cool thing that was introduced at about 1984 based on this observation. It's called the weak generational hypothesis, and it is most objects die young. It means soon after I allocate stuff, most of the stuff I allocate will die. Now, don't equate this with most live objects are young or anything like that. Most live objects actually tend to be old because they're the ones who survive. But dynamically, out of every 10 objects I allocate, 9 will die or something like that. And that's a very strong observation. It's usually more than 10 to 1. Knowing that this is true, or believing that this is true, we can apply what we talked about in efficiencies to make a very efficient generational collector. The way we do that is we focus on what we call a young generation, the region of memory that was recently allocated, believing that the vast majority of this is dead. The vast majority is dead means the live set is a very small percentage of the heap size. So I want to pick an algorithm that's linear only to the live set and not to the heap size, and that will gain efficiency. As long as they were of similar size, 2x here or something, but if I think that only 1% or 0.1% is alive, and I apply a copy collector to that, that's 100 times more efficient than a sweeping collector is. If this stuff is dead. Now, how do we keep this stuff true? How do we make sure that this assumption remains true? Things do survive, and if we keep them in this thing, they'll keep accumulating, and this sparseness will stop being true. So things that have been around for a while, we have to put somewhere else. We need the young generation to be young, because this assumption is true about young stuff. And that's what promotion is. Move stuff that has been around long enough somewhere else so we keep being efficient in the young generation. Now, there are places where I've seen people tweak the young generation to with size and promotion thresholds to never promote, or to try really, really hard to not promote. All they're doing is making a single generational collector where there's no weak generational hypothesis and all the efficiency is out the window. You have to get rid of the objects for the efficiency to be there. Once we get rid of them and put them somewhere else, we collect that somewhere else, the old generation, when it fills up, with whatever collector we choose for that. And this tends to be an order of magnitude plus filter. So today in most workloads, I mean the vast majority of workloads, every workload I look at a GC log for, we're looking at a 10 to 1, 20 to 1 ratio between the work we need to do if we have a generational collector and if we didn't for the same algorithm. It's a pretty effective filter. There are a few other things about it. To do this magic, we need to maintain something we call a remembered set. We need to know about the roots into the young generation so we can only look at the young generation and not at the whole heap. If we looked at the whole heap, game over. So we do that with something that lets us know about all the pointers from the old to the young. There are various techniques for that. Card marking is one of those, and I'll talk about it a little bit. The other nice thing about generational collection is we can use something like a copying collector for the young generation, but not have 2x the memory in there, because if we can't fit the entire from space in the to space, we'll just spill it over to the old gen. But the young generation doesn't have to be twice the size of Eden. This is why if you look at Hotspot, for example, the Eden tends to be much larger than the survivor spaces. It's not that you know it's going to fit there, it's just if it doesn't promote. Okay. So remembered sets are these important things that we won't cover here. The little I'll say about them is this. In order to track all the pointers from the old generation to the young generation, we have to intercept anything that stores such a pointer, or scan in some other way that probably will be less efficient. This is why there's a write barrier in most collectors that are generational that tracks all pointer writes so that it could keep track of the set. The base assumption is this set is very small, sparse. If most of the old gen pointed to the young gen, the weak generational hypothesis is probably wrong to begin with. So it tends to be very good and very efficient to work that way. And card marking, which is a technique that's used by all the JVMs I know of, seems to work well. Now, if we put all these things together, we talked about terms and mechanisms. Let's look at how they come together into actual collectors. The young generation, all the collectors, all the current production collectors are generational. There's some non-generational or hybrid generational. I'm very interested in your talk later that explains how you can half do a generational. That are not, but in the production systems, this is absolutely true. The young generation is usually a copying collector, and it's usually a monolithic stop-the-world copying collector. Every word on this slide has been defined now. Okay, these are terms that we talked about, not just made up words. The old generation is usually some form of a mark compact. May sweep, may not. The old generation might be stop the world, might be concurrent, might be partially concurrent, might be incremental, stop the world. There are all kinds of combinations. This is usually where a lot of the interesting differences are. Now, if we look beyond just those classifications of stop the world and stop the world, would be simple. There are a few non-stop the world techniques that have been out there for a while. For example, what if I want to mark without stopping the world? The G1 collector, the CMS collector do this. One way to do this is to deal with the simple race that happens if you do it and plug it up. The simple race that will happen is if I'm going around marking, painting everything I can see, and you, the mutator, is picking up an object I haven't looked at yet and puts a reference to it behind me in a place I've visited and won't visit again. And then get rid of all other references to it. I might not see the object. Might not mark it alive, might collect it, even though it's alive. And that would be embarrassing. So we have to plug up that concurrent marking race. And there's only one real concurrent marking race that needs to be plugged up. Somehow we have to prevent that propagation from something I haven't seen to behind me to what I visited. One of the common ways to do this is with multipass marking. The idea there is you track every mutation of every pointer in memory. Every time you write to a pointer, you track that. And then when you finish your concurrent pass, you say, well, that's probably good, but I've missed something. So let's look at everything I've mutated and work on that. And when you finish looking at all the stuff that you've marked as I've touched this, maybe you're done, but maybe you need to do it again. When you feel good about it, when you think the list is small, you might stop the world and finish the work. Depending on the algorithm you've used, you may be able to make this converge provably or not. The CMS collector, for example, just retries and we'll have some unknown amount of working set at the end, but the G1 collector uses a snapshot at the beginning marker that can prove that this converges. But these are techniques that, as an example, they involve tracking mutation as you write. Every write to the heap now costs you. The other interesting thing you could do is try to not compact the entire universe at one time if you agree that compaction will happen. And then you try and do incremental compaction. This is fundamentally what G1 does. What does that mean? We track the cross-region stuff, the pointers between regions, as a different kind of remembered set. And then we try and find regions that have only a few other regions pointing to them, or sets of regions that point to only a small set of regions. We compact the target regions knowing that I only need to fix up pointers in a small set of regions rather than the whole heap, and I hope I could find those sets. This actually works pretty well, but it could run into degenerate behaviors where you end up with a very empty region with a very popular object in it, so you're not going to compact that. Then you'll do the same for other regions, and eventually you have to compact a tiny bit of the heap and live in it. So those are fundamentally improvements, but they're part of what I call the denying the inevitable trend of garbage collection in general. We start with some understanding that you can't get away from compaction. And then we basically say, let's go after the empty spaces or the cheaper spaces to get stuff from first, and we apply a generational collector. That's a great efficiency technique. It also reduces pauses until we have to do the whole gen. But eventually you have to do the whole gen. So then you look at the whole gen and say, well, I don't want to compact that whole thing. Maybe I can avoid compacting it. Maybe I can keep things in free list for a while until I have to compact it. That's what CMS does. But eventually, you're going to have to compact it. So you look at that compaction and say, maybe I won't have to do it all at once. Maybe I could do it a piece at a time, and that's what G1 does. But eventually, you're going to have to deal with popular objects and other pressures on the heap that come out of that. If we look at the actual collectors you deal with today, here's the classification I said most of them will fall under. Let's start with parallel GC. Parallel GC is a classic parallel collector, has a parallel, monolithic, stop-the-world copying UGen. Pretty much everything I say is parallel, by the way, now. So. It also has a monolithic, stop-the-world, mark, sweep, compact UGen. It's pretty much the algorithms I talked about before. It's efficient, it's fast, it stops the world for everything it does. Let's look at the CMS, concurrent mark sweep collector, a common collector used for pause-sensitive applications. What do you guys think the young generation collector of the CMS collector classifies as? Yep. But what kind of copy? It's a monolithic stop-the-world copying collector. It's exactly the same algorithm classification as the parallel GC. What does that have to do with CMS? Well, nothing. CMS is named for its old generation behavior. The young generation is a monolithic stop-the-world collector. It is not concurrent and it is not mark sweep. The old gen is a mostly concurrent, described so in the academic paper that describes the algorithm, mostly concurrent, non-compacting old gen. It's got this multipass marker that's mostly concurrent. It's got a fully concurrent sweeper, keeps things in free lists. And then it has this doesn't compact part, which is where the mostly comes in. Because you can't get away from compaction, so that's what it does when it has to compact. It does a monolithic, stop the world, mark sweep compact. The CMS part is a filter between the new gen and the full GC. It's an effective filter, but eventually you'll hit the full GC. This is a big reason G1 exists as a collector, because of the realization that you can't get out of compaction. So let's look at G1. What does the new gen of G1 classify as? G1 is an incremental, garbage first thingy. Well, it's a monolithic stop-the-world copying collector. You notice the pattern here? Its all-gen has a mostly concurrent marker, but it's a much better mostly than the other marker. It is provably, it'll provably converge. So you can't run an application that will make it run forever. But it has a stop-the-world, mostly incremental compactor. It does not compact concurrently. It stops the world for any compaction. And the only way it frees memory is to compact. So the only way it frees the memory is to stop the world. But it tries to do that in small increments. Now, I actually have a quote here from the objective, the design objective of the collector. It says, we try to avoid as much as possible having a full GC. What does it tell you right there? That it has a full GC. Design, by design, it's designed to have a full GC as a fallout, the fallback from trying to do the right thing with incremental as long as you can. But you will end up there. Maybe it'll take longer. Maybe you can tune stuff so for your application it won't happen for a long time. But by design, there's a full GC. Okay. How are we on time, by the way? Okay. Yeah. So I classified the normal hotspot collectors, the ones you can use today. I'm going to talk a little about this monolithic stop-the-world GC problem, or the stop-the-world in general. Now, there are many ways to deal with stop-the-world GC. This is the most common way to deal with stop-the-world GC. So, you could just go to the other talks that talk about how to tune things. Right? Imagine that this is not a problem, or maybe we'll tune it so it'll run this long without a GC. We'll declare success. 40 minutes, no GC, yay. But then you look longer and you see that there are glitches, and you look over days and you see that there are regular glitches. Another way is to use creative language to make yourself feel better about the fact that you have stop-the-world GCs that'll just freeze your entire application for no good reason except for the collector wants to go on vacation. These are actual sentences from marketing material and design goals on the web, by the way. I'm not making any of these up. This is from an actual marketing material of a JVM I can't name, but I could say that it has something to do with determinism. And that had a brilliant sentence. It said, I will guarantee a worst case of 5 milliseconds 99% of the time. Doesn't that sound great? It's a guarantee. I'll just point out that 1% of 1 hour is 36 seconds. I'm allowed to pause for 36 seconds once an hour, and I've met my guarantee. Or I'm allowed to pause for 360 milliseconds every 10 minutes, or whatever those are. And, you start having to have, that's a meaningless statement that makes you feel good. But there are others, mostly, as I said, put mostly in front of stuff. Makes people feel good. That's what it means, right? So that's what it literally means. It's telling you right there. It's honest. You just want to read it the other way. You don't want to hear about the rest, right? Fairly consistent. I've heard this a lot. It's a goal. That's actually a JET goal for a future version of G1 to be fairly consistently below 500 milliseconds. That literally means that sometimes we will be worse than this, right? We'll be way outside the range. And typical pauses will be in the tens of milliseconds. Literally means we will have pauses much bigger than tens of milliseconds. We told you so, right? So these are good ways to make you feel good about them, but if you actually have to make an application live in the real world, you might want to actually measure what's going on. And one of the tools you might want to look up is JHiccup. It's on GitHub, open source everything, and it lets you view the actual hiccuping behavior of your application. Oh, we are done on time, so it's not 15 minutes. I'll do 2 more minutes then and quick. Sorry about this. So C4 is a collector we have. It solves this problem. The problems that need solving, you can look up the slides online later. But fundamentally, if you classify it, it has a concurrent guaranteed single pass marker, can't beat it, and a concurrent compactor. It classifies as compacting, a concurrent compacting all-gen and the concurrent compacting U-gen. It's the only non-pausing new gen there is right now in JVMs or runtimes in general. It has no fallback to stop the world. We don't have code that knows how to do this. So there is no full GC, there is no stop the world, there is no I couldn't do it, so we will pause instead. Design-wise, it's built around the notion of always doing the same thing and never being in a hurry. A lot of the algorithm design is to make sure this is true. And I will jump forward here. I apologize for the time management here. Algorithm cool things. You can see this online if you want. We have plenty of material on it, but let's talk about what it does to your application. The fundamental thing is we take care of things like GC tuning. So you no longer have to do this or this. Instead, you just do this kind of stuff. And tune the heap size down until it breaks and then triple it and go home, right? So, tuning GC looks like this. You get behaviors for real applications where this is Cassandra running on a regular server. That's the 1 millisecond line for pauses. And you get to run applications with just more throughput per machine if you care about SLAs. You just get more out of a machine if the reason you put more machines to work is the SLA isn't good if you put too much work on it. So fundamentally, that's what C4 does, and it is a concurrent, young gen and old gen collector. You can come to our booth, you can come talk to me after here as I clear the room for the next speaker. And I'm sorry for the surprise on the time here. I thought we had another 5 minutes. So thank you.